go live. Okay, good afternoon, everyone. Welcome again to Warsaw University Astronomical Observatory Tuesday seminars. And today we have a guest from Wrocław in Poland, Piotr Kolaczek-Szymanski, who is a newly born doctor. He just defended his thesis, and he's going to tell us about his research from his thesis about eccentric binary system. I'll just mention that Piotr is now still working in Warsaw, but is moving to Liège for his postdoc very soon. So it was a rare chance to have a newly born doctor and tell us about your work. Piotr.
Thank you, Łukasz, first of all, for your very kind invitation to this place. This is not my first time in your observatory, of course, but I remember it very warmly from astronomical student conferences. I was there many times, but this is the first time when I'm here standing on this particular floor, and I have an opportunity to give you the talk about mainly some of the results from my PhD thesis. But when I was thinking what I should tell you during this talk, I had an idea to present some broader context around all eccentric binaries. So let me begin with this very interesting plot shown here, because some of you should know this plot very well. It shows you the multiplicity fraction and companion fraction of main sequence stars, or at least close to the main sequence, in the very broad range of masses. So you can see this very interesting trend, which tells you that the binarity is really important, and it is something inherent for massive stars. This is why the evolution of massive stars, or even intermediate mass stars, is inseparable from binarity. So we cannot neglect this kind of phenomenon when we are trying to, for example, predict evolutionary paths of especially massive stars. And there are many interesting objects and phenomena which are directly related to binarity among these stars, so with intermediate and high masses. First of all, we have 1B or 1C type supernovae. They are especially connected to binarity. Then we have something which begins to be a trend, or there is some kind of a fashion nowadays in astronomy. These are street stars. We are looking for street stars, so stars with which lost the major part of their hydrogen-rich envelope. And of course, we have closed binary systems, which consist of compact objects, and these are natural progenitors of gravitational waves. This list is, of course, much longer, but at least I would like to show you these three examples. First of all, I would like to say a few words about eccentric ellipsoidal variables, and this animation prepared for you in TV shows you the general concept of EEVs. I will use this abbreviation EEV for eccentric ellipsoidal variables. Basically, we have two stars which are revolving each other in an eccentric orbit, and the combined effects of ellipsoidal variations, the irradiation effect, and Doppler beaming will produce this beautifully looking light curve, which shows very significant variations near the periastron passage. And of course, the shape of this light curve will depend on the orbital parameters of the system. So as you may see, some of these light curves can resemble the electrocardiogram, and this is why these systems sometimes can be called as heartbeat stars, although there is some confusion in the nomenclature, in the literature, because heartbeat stars, there is no clear definition of this group. So that's why I like to use this more specific term, which are eccentric ellipsoidal variables. And this artistic vision of such system shows you strongly distorted stars. You may ask why it's so important to study EEVs. Maybe it's something which is irrelevant for current state of astrophysics, but it is definitely not, because our prediction about the evolution in binary systems is strongly affected by our knowledge about tidal dissipation phenomena. And this is why we cannot predict evolutionary tracks of binary systems very accurately, because I don't know if you are familiar with tidal theories, but they are quite old, and there are many parameters which aren't related directly to physics, so we can tweak them, switch them, increase some of them, and we can get anything we want. That's why any studies which are dedicated to binarity and to tidal interactions are really vital for theoretical studies of binary systems. Okay, and the second phenomenon, which is connected with EEVs, are tidally excited oscillations. I will use this abbreviation TO to describe them. This is a more sophisticated phenomenon. This animation was prepared by Rich Townsend, thanks to Mesa and Dyer codes. So the heartbeat effect is the effect caused by equilibrium tides. And we have two types of tides. We have an equilibrium one. So this is a static response of the stellar volume to changing or varying tidal potential. And the second one is a resonant phenomenon. We call it dynamical tides. And this kind of tides is shown here. So we have a companion, which is revolving the main component in this binary system. Of course, we have an eccentric orbit. And at the bottom of this plot, you can see the light curve, which shows the heartbeat. So this central variation at the plot is caused by the equilibrium tides. Let us call it the standard tide. But outside the periastron passage, you may notice that there are also some variations, some pulsations, which are present through the entire range of orbital phases. And these are TOs. So basically, when the component is exciting the stellar surface or the entire stellar volume every periastron passage, we can see that if the eigenspectrum of the modes will coincide, at least one of these modes will coincide with one of the harmonic frequencies of the orbital frequency, you will get the resonance between those two, between this resonance eigenfrequency and this specific orbital frequency harmonic. So it behaves like a droplet, which was excited by, for example, some sonic wave. Yes, you see oscillations which are coherent with the orbit. This bunch of plots shows you the composition of dynamical tide on specific eigenmodes with different frequencies, but each of these frequencies is the exact integer multiple of the orbital frequency. So when we are observing heartbeat stars, EEVs, we can sometimes notice the pulsations visible in the light curves, which are phasing with the orbital period, and that's why we may be almost 100% sure that these are TOs and not some, for example, self-excited ordinary oscillations. Okay, you may ask a question, why should we care about these TOs? Because normally we use pulsations to study the interior of the star, yes, to probe some regions like the stellar core or the transition region between the core and the envelope. But because tidally excited oscillations are coherent changes with the orbit, they will take part in the evolution of the entire orbit. So there is some kind of a coupling. Battery is dying. My battery is dying. Ah, yes, because I had a question where I can plug this one. I didn't see a power socket anywhere. Okay, thank you, Marcin. Yeah, it would be a disaster to set it up properly. You have 2 minutes. Okay, thank you. Thank you very much. Yeah, coming back to my talk. So this time we don't have just self-excited oscillations, but we have something which is coherent. So these oscillations can transfer the energy and the angular momentum with the energy and angular momentum of the orbit. So, for example, here you can see some kind of an experiment made by Vita and Savonier, where you see the evolution of twin binary system consisting of two 10 solar masses star. We are starting from the orbital period equal to 5 days. You can also notice that the eccentricity at the beginning of main sequence is equal to 0.25. And now we are trying to predict the evolution of the entire system, but with the inclusion of dynamical tides. So we don't have this standard Chance theory about equilibrium tide, but we have something additional. So in some epochs, you may notice that the character of this change changes dramatically. And this is because a strong resonance and resonance locking between one of the eigenmodes and one of the multiples of the orbital frequency. Okay, so the actual evolution of every binary system which has non-zero eccentricity is not how to say it in English. It's not a curve which is smooth. It's more like a staircase or something like that. So this is the true evolution of binary system, not the smooth one. And the second plot I would like to show you is something which is almost purely observational, because this plot shows you the distribution of orbital periods and eccentricities of binary systems which contain G-type main sequence primary. As you may see, this distribution is bounded by this thick dashed curve. And this is the comparison between two very different phenomena. This curve is the prediction when you are using only equilibrium tides, so the standard theory by Chang. And this one is the curve predicted when you include the effects of dynamical tides, and that sometimes we will have resonantly locked TO with the orbit. So as you may see, it's almost impossible to reproduce this kind of distribution without dynamical tides. Okay, so it's not a negligible effect. We have to care about TOs, about dynamical tides, to understand, for example, the distribution of this kind of binary systems. Okay, so the almost all part of my PhD thesis was focused on searching for EEVs and TOs, and now I would like to show you just a few examples. I think main results from my thesis. The first one is connected with looking for TOs in test data. So before the test era, we knew only about, I think, maybe 100 heartbeat stars coming mainly from Kepler observations. So this sample wasn't too big. And the first idea was to search for this kind of binary stars and search for the TOs in test data. We found about 20 new massive or intermediate mass heartbeat stars. They are all listed here. And here I just show you some of the example light curves from this sample. The main goal of this paper was to populate this diagram with heartbeat stars, because thanks to Kepler observations, mainly thanks to them, we knew around 100 EEVs located in this mass range. I hope you can see it. There is the logarithm of the total mass of the binary system. So from Kepler, we detected only solar-like EEVs with some portion of EEVs with red giants. And there were only a few known EEVs that are really massive. This one is a monster, this Machon, I will talk about this very interesting extreme system in a couple of minutes. And all these points, which are shown with pale blue color, are coming from our study. So before work done by Marcin and us, it was maybe not a revolution, but a significant change, because thanks to this work, we found many new massive EEVs. Okay, and now I would like to show you just a few examples of those EEVs which show TOs. So, for example, this HD star with this horrible number, you can see a heartbeat. This is this smooth change across the entire phase range. And when you subtract these changes from the light curve, you can notice that there is some variation, periodic variation, which fits very well with the orbital period. So in periodogram, you will notice clear peaks located in the 9th, 7th, and 18th integer, 18 times the orbital frequency. Of course, this is a clear sign that we observe TOs. The only trick is to properly model these changes, I mean the heartbeat changes, because if you will make it, if it will be not correct, you will of course see a whole set of frequencies located in a harmonics of orbital frequency. But in this situation, you can be quite certain that we observe TOs. The second example is θ1 crucis, where you also can notice a very sharp heartbeat variation. And after the subtraction of this signal, you can notice very beautiful TOs in the entire range of phases. Okay, what's interesting, heartbeat stars can also show, not stochastically, but self-excited oscillations. So the standard type of oscillations located outside orbital frequency harmonics. And the interesting question is, if there is some coupling or interaction between TOs and self-excited oscillations. It may be interesting when you're dealing with, for example, with topics connected with angular transport inside the stellar interior. Okay, because Marcin probably had many opportunities to present the results from his work and his collaborators, of course, about the Ogle collection of nearly 1,000 heartbeat stars. I will just show you as a reminder that there is such a paper, 2 papers in fact, where we found nearly 1,000 EEVs towards the galactic bulge, of course, and towards Magellanic clouds. This is a gallery of these binary systems. But what's important, the majority of this sample consists of systems which contain red giants. So the amplitudes are quite huge. Like for EEVs, because you may notice that the I-band amplitude, I think it's a total range of brightness variations. Correct me if I'm wrong, Marcin. It's about 0.1 magnitude, so it's a huge change in the brightness. Okay, and this is my part of the job in these papers, because I was interested mainly in searching for TOs in this collection of heartbeat stars, and we found them. Surprisingly, we didn't find many TOs in massive systems, or systems which contain main sequence components, but a huge part of TOs which we found in these stars are exhibited by red giants, and this is something very exciting, because as you may probably know, when we observe TOs or when we model TOs, this is not an extraordinary astroseismology. We call it tidal astroseismology, because this time the pulsation is pumped every periastron passage. And the set of these TOs which we observe in red giants in future will allow to perform for the first time this kind of analysis, I mean the tidal astroseismology, for red giants. It's very difficult. That's why until now it's not done. But I think that some groups we are dealing with mixed modes in red giants will finally examine this kind of oscillations. Okay, and the third paper which I prepared with Tomek Różański, also from my university, was to examine if TOs occur in some particular evolutionary phases. This paper was purely the theoretical one. So we made such an experiment where we generated hundreds of binary systems with MESA binary package, and then we were tracking their evolution until the end of the main sequence. And every time step, we calculated the eigenspectrum of each component, and we checked if any of these oscillations was coinciding with the integer multiple of orbital frequency. So this set of curves, I will call them resonance curves, show you basically that when the value of this curve is really high, there is a great chance to excite TO in this system. And as you may see, these curves are always plotted for two components. So sometimes you may observe, you may have the situation where many of TOs are excited at near the terminal age main sequence, and sometimes you may have a lack of this oscillation. So the possibilities are endless, and to classify somehow this behavior, I mean this resonant behavior of binary systems, we summarized all of the thousands of these resonance curves with the UMAP manifold projection. And these projections, these manifolds, just two-dimensional, are showing you the manifolds correlating with the morphology of this resonance curves. So as you may notice, for example, the resonant behavior of a binary system correlates very well with the initial separation at periastron near the zones and with the initial eccentricity. And the secondary effects are mass of the primary component and, for example, the rate of rotation. Okay, this is some kind of a gallery. When you are traveling on this manifold, you may meet many examples of these resonant curves. Sometimes during the whole life on the main sequence, the system may undergo just a few resonant phenomena, so just a few TOs may be present in this system, but sometimes you may have plenty of them. So we have many possibilities. Okay, and on this plot, in this plot, I would like to show you what's the mean rate of TOs in massive and intermediate mass binary systems. So these R symbols are just mean rates of TOs per 1 megayear versus the mass of the primary component and the secondary component. As you may notice, there is a slight trend towards the higher masses. So if we have a truly massive binary system, we can expect that this system has the statistically highest chance to observe a TO in them, because in the particular time when we are making an observation, we have the highest chance of observing it. Okay. And you may also ask me which evolutionary phase is most favorable one to excite TOs. As you may notice on these plots, 0 means ZAMS and 1 means TAMS, so terminal age main sequence. Most of these resonant phenomena will arise near TAMS. So when you have a massive star, it evolves through the main sequence. When it will reach terminal age main sequence, you may suspect that many of TOs will be excited in relatively small period of time. Okay, of course, there are many problems and limitations. So now I would like to end this, this part connected directly to my PhD thesis and show you at least 2 examples of limitations that we have to hit when we deal with eccentric binaries. The first one is the Roche model. So the only codes which allows us to model both radial velocities and light curves simultaneously for binary stars are Wilson-Devigny, I think this is the most popular code, and Phoebe. Of course, both these codes rely on Roche approximation. So this is the approximation where we have just a point-like mass, which is located exactly in the center of a star, and then we model the tidal deformation of the stellar surface by saying that this stellar surface will coincide with one of the equipotentials. And the recent paper by Felay and Dupré, I don't know how to say it properly because this is a French surname, shows the discrepancy when you model the system with a hydrodynamical method and with Roche model. So we have a twin system consisting of 2 low mass main sequence stars, and as you may see, this yellow curve will shows you the location of the surface when we apply the Roche model, and this purple curve shows you the situation when you will make very exact calculations. So the mass is distributed actually like this in a real star, and you may notice that the deformation is always higher near the L1 point than the model with Roche approximation. So when these authors constructed such a measure of this discrepancy, it's called delta R, as you may see. So basically, it's just a difference between the radius towards the stellar surface near the L1 point, okay, minus the deformation for the Roche model, and divided by the difference of the deformation for Roche model minus the radius of exactly axially symmetric star. As you may notice, this difference, of course, it depends on the separation of both stars, of the separation between them, and it tends to some limit. So almost exactly always we have a situation when stars are actually more deformed than the Roche model tells us. And this discrepancy very strongly increases when the system becomes to be compact one. So this is a huge limitation because now we are dealing with photometry, which is mainly spaceborne photometry. It's of very high quality. So when you have a goal to model such a system on a sub-PPT level, or at least PPT level, you will hit this wall because this difference, which I was showing just on the previous slide, which will translate to 1 PPT or maybe few PPT difference in the light curve. So I think all of our models, I mean, for example, radii of both components are biased in some direction because we always model our binary systems with Roche approximation. But it's untrue, of course, and we have to create a second generation software for binary stars where all of these tidal deformations would be calculated. Will be calculated in the hydrodynamical manner. Okay. The second complication I would just very quickly show you are nonlinear tides. So if you remember TOs, they are coherent oscillations, coherent with binary motion. You can imagine the situation when the periastron passage is so close to the primary component that this wave, which is excited by the tidal potential, will break due to some non-linear processes. And there is a paper, very recent paper, by maybe not very recent, but from 1 year ago, by MacLeod, et al., which shows this kind of phenomena when you have a red giant and a very close periastron passage. So TO will be excited in such a system, but because the amplitude of this TO during every periastron passage is so large, this wave will break. Okay, so it's not an oscillatory motion, and the wave will try to find some kind of an equilibrium. I will run this simulation once again from the very beginning. So this small black cross shows you the location of the secondary component. The star in the middle is a red giant, and we can see this beautiful TO, but unfortunately it's non-linear TO. We don't have any kind of software which could simulate the same phenomenon, but in terms of the light curve. So, for example, maybe in this collection of 1,000 heartbeat stars from Ogu, which contains maybe red giants, some of the stars have components which are passing the primary components so close that maybe this huge amplitude is due to non-linear breaking of dynamical tide. That's why some of these stars can have non-repetitive behavior every periastron passage, because this is very turbulent phenomenon, and it will not stop after a few periastron passages. I have to warn you, because we have an envelope which is inflated. The mass contained in this envelope is really small compared to the core, okay, at least some outer layers, and only the outer layers are affected by this phenomenon. So you can have thousands or maybe even more times periastron passage, which will cause this kind of phenomenon in binary systems, in EEVs, sorry, with very massive, with very inflated components. Okay. Yes, and in some cases, we can also have a problem with distinguishing heartbeats from other kinds of variability. Sometimes heartbeats with intermediate values of eccentricity may behave like rotational variables. We can show even such situations, but there is one system which is really important for me and for my study, for my research I'm doing right now. This is macho with this number, and for reasons that will be clear in a couple of slides, I will refer to it as extreme ellipsoidal variable. So this is the light curve of this system. As you may see, every periastron passage you have this nice heartbeat-like feature. This system is an SB1 type eccentric binary system located in the large Magellanic Cloud. Sorry. The V brightness is this is quite faint for tests, but at least we can make some spectra for this star. The primary is a blue supergiant with emission lines, so we can guess that this is relatively young star, which is massive. Okay. The orbital period is around 32 days. It was discovered in Macho survey. It was classified as an eclipsing binary system. Then many days later, it was rediscovered by Jayasinghe and his colleagues in 2019 and classified as an eccentric ellipsoidal variable, so extreme heartbeat star. And the total range of light changes in this system is really extreme, because this is around 0.4 magnitudes. This is an enormous range of brightness changes for EEVs. I don't know if you remember these slides which were showing results from Marcin, but even for systems for EEVs containing red giants, this range of light changes is around typically 0.1 or below magnitude. So here we have something which is much smaller, because this is a blue supergiant, yes, so the size is much smaller, but the range of brightness is really huge. I mean, it's much greater than typical amplitude for an EEV with red giant. So that's a mystery to solve. We observe tidally excited oscillations. I will show it in a couple of minutes. And this is the first heartbeat star where TOs significantly change their amplitudes and probably also frequencies. So the main problem in this system is how to explain this extreme amplitude if this is truly an EV. Just to show you this beautiful TOs, so after the subtraction of stochastic variability in this light curve and this continuous heartbeat signal, you may notice that some of the frequencies are significant and are correlated with the position of integer multiples of the orbital frequency. These are, of course, TOs. So we have a TO with 23 times F orb, we have 25 times F orb, and so on. But there is one frequency which is truly extraordinary, because this TO has a frequency which is equal to 230 times the orbital frequency. And that's a mystery, because from theoretical point of view, it's impossible to excite such a TO in such a system. The eccentricity is around 0.5. So maybe this TO arises from strange modes. All of you are probably familiar with types of modes. We have acoustic modes, we have gravity modes, we have mixed modes, but in inflated, radiation-dominated envelopes, we also can observe, or at least we expect, the presence of strange modes. These are very highly non-adiabatic stellar modes, and this TO has some properties which fits this picture. So it would be the first TO arising from the excitation of a strange mode. Okay, and these are the changes of their amplitudes and frequencies. So when we compared the phased light curve of this XEV in the first year of test observations and in the third year, because there was a gap, 1 year gap in the middle, we noticed that TOs significantly change their amplitudes. So this is the first system where you have the excitation of a TO every periastron passage, but some phenomena change the amplitudes of these oscillations. And this is really weird, because normally when we observe stars which are pulsating due to self-excited oscillations, it's quite standard, it's quite normal that these oscillations will change amplitudes due to some, for example, non-resonant, non-linear mode coupling, etc., etc., etc. But when we observe TOs, they are excited every time, every periastron passage. So this is a question why, for example, this TO, the amplitude of this TO is dropping very rapidly. I mean, in a scale of months. So you need just several months and the mode decreased the amplitude by more than 50%. Okay, so we made soul spectra for this object and gained 16 useful spectra at SALT HRS in 2021 and 2022, and significantly improved the ephemeris for this system, because when we are trying to solve this puzzle, we have to know exactly the geometry of this orbit. I mean, the omega, eccentricity. We also have to know time of periastron passage. So we are quite certain that this system is an eccentric one with eccentricity around 0.5. And we also know exactly the omega, the time of periastron passage. Maybe there is also a third companion, because as you may notice in this picture, we have some kind of a parabolic trend in radial velocities. So it's quite normal for massive stars that they reside in multiple stellar systems. Okay, so because we know these parameters, we can estimate somehow masses of both components. So we generated the 3D model for this system. And as you may see, it completely cannot fit the amplitude and the shape of this variation. So this kind of variability observed in extreme heartbeat star cannot be explained with an ordinary model, at least this coming from Phoebe or Wilson-Daly. And we were trying to explain these changes due to some presence of, I don't know, some outflowing disk, because this is a blue supergiant. So typically blue supergiants do have outflowing disks from their equators. But thanks to salt spectra, once again, we fit these models, and we check the positions of these disks, which emits the radiation in H alpha, H beta line, for example. And the disk was ruled out because the location of this disk is in collision with the secondary component, so it won't be stable. Something different is going on. Something different is going on in this system. The second interesting thing is the amplitude in different passbands, because maybe we were asking ourselves if this system is a system with non-linear breaking of dynamical tides. So maybe this is exactly the phenomenon where you have such close periastron passage that the steel is non-linear, the wave breaks, and that's why we see so huge range of light changes. But this is not the case, because in such a situation, I mean the situation with non-linear wave breaking, there would be very, very strong gravitational darkening of this wave which breaks on a surface, and it would result in very significant behavior of the light curve in different passbands, especially in the U filter passband. As you may notice, thanks to Las Cumbres Observatory and Opticon observational time, we collected these light curves for XTEV, and we noticed that we don't see any changes in this brightness, in the brightness changes. So whatever is causing these fluctuations has some gray nature, let us say. Okay, so both in the mid-infrared passbands, like TESS, for example, and in the U passband, we have exactly the same amplitude. So maybe some Thomson scattering is involved, because it suggests some phenomenon which do not depend on wavelength. Okay, so we were suspecting that it may be a wind-wind collision binary at this point. But now I would like to show you another evidence that it's really a wind-wind colliding binary. First of all, we collected infrared measurements for this star and examined the location of EXTV shown with this cyan or aqua star on this plot. And we noticed that it does not behave, like BE supergiants. So despite we have, although we have emission lines in the spectrum of this star, it does not have an outflowing disk, because if the disk will be present, the star should be located somewhere here on this near infrared diagram. And we also noticed that this color index, which for supergiants correlates very strongly with the mass loss rate, I mean the mean mass loss rate, suggests that our star is losing mass like an AGB star. So maybe this is a wind-wind colliding binary. The same is, of course, also visible in the spectral energy distribution. You can see very nicely the slight excess in near infrared and a huge excess of light in the mid infrared. So there is a lot of, let us say, cold dust, which is located outside this whole binary system, but we do not have a huge amount of warm dust normally present in BE supergiants. Okay, and we also noticed that there is some additional absorption feature in this system. So to properly model the spectral energy distribution in both near UV light and in short wavelengths of visible spectrum, we had to add this additional broad absorption feature to standard Fitzpatrick absorption curve, galactic absorption curve. I think it may arise from, because the conditions which are in this disk which surrounds the entire system are very different from the interstellar medium. Maybe there is some kind of a production of molecules or dust which do not fit ESM, and this additional feature arises from untypical composition of such a dust, which is revolving the entire system. Okay, so at this stage, we made an assumption that these huge light changes are due to wind-wind collision in a binary system. A very similar phenomenon is observed in very massive star R144, located, of course, in the Tarantula Nebula, where we observe very similar changes, yes, like in our heartbeat, let us say, but these changes are due to atmospheric eclipses. So these are not ordinary eclipses, not ordinary photospheric eclipses, where you have just a star which is eclipsed by another, but you have a system with relatively low inclination angle and very strong wind coming from the primary component, and the secondary can be occulted by this intense stellar wind. So this is an atmospheric eclipse, and the excess emission comes from the wind-wind collision cone. This is this abbreviation WWC. And this collision can be seen, for example, at this animation. So basically, when you have a primary component with very intense, very dense stellar wind, the primary plunged into this wind, and the shock wave forms at the boundary between those two winds. So you may observe, for example, very intense X-ray radiation from this hot shock. And you also can observe some kind of an excess because this boundary is very dense. It is highly ionized, almost totally ionized. So we have many of the free electrons in this gas, and you can observe the light which is scattered from the luminous primary companion. That's why you may observe this excess of radiation. And the combination of these two effects may result in a light curve which mimic heartbeat. So when we are dealing with heartbeat stars consisting components that characterized with strong stellar wind, we may suspect that some of them will not show changes connected with ellipsoidal variations, but this variability will be almost completely due to wind-wind collision. Okay, so this is the geometry of our system. I mean, both the orbit, the orientation of this orbit, the eccentricity, and the sizes of the components are to scale in this plot. So we have a secondary component which is much smaller, the primary component with around 30 solar radii with a dense stellar wind, and the high amplitude TOs present in this system. And the presence of the close component probably enhanced this wind. So it's so dense that we can observe both the atmospheric eclipses and the collision of stellar winds. And that's why we see both atmospheric eclipse when we have a superior conjunction. Then when we have a periastron passage, this wind-wind collision cone is very dense, so it can scatter the light. It can also emit its own light due to the high temperature. And when we have the inferior conjunction, the secondary component is partially eclipsed by the wind-wind collision cone. That's why these 3 points, A, B, and C, translates to these moments in the light curve. And we can, and we constructed such a model for this system. So this blue line shows you the model fitted to this observational data. As you may see, the fit is satisfactory, as we usually say when we show something like this. Thanks to this depth and the width of this atmospheric eclipse, we can obtain the inclination of the system, and we also obtained the mass loss rate observed in this system. I don't know if you are familiar with values, with typical values for massive stars, but I should see a shock in your faces, because it's a really, really high mass loss rate. Normally, in massive stars like, I don't know, blue supergiants or Wolf-Rayet stars, we have mass loss rates at the level of -6, -5 maximum. And now we have a system which is quite near the main sequence, and the mass loss rate is typical for an AGB star. So this is an extreme effect for such a system, okay? Because probably this is one of the examples. I have to check the literature, but probably this is the first example of a system where we have a very strong evidence that the binary, I mean the presence of the secondary, enhance this mass loss. Normally, if the star would be a single star, this mass loss rate would be on the level of -6, -5 at maximum. Okay, our model, of course, do not account for the eclipse of the secondary component by this wind-wind collision cone. And this is the reason why we observe in the residuals around the inferior conjunction this drop in brightness. So this drop is due to the wind-wind collision cone, which occurred the secondary component. Okay, so at the end, I would just show you that the estimation of masses for such objects is very difficult. If the standard procedure for estimating masses, if we have an SB1 type binary, is to just place the primary and secondary and the primary components on HI diagram and check these evolutionary tracks with what range of masses we can deal with in this situation. So it's very hard to tell what was the initial mass of the system, but as you may see, it can be between 25 and even 60 solar masses. But currently, this system probably has a mass between 30 and 40 solar masses. So this is truly very massive system, and a very rare situation where after leaving the main sequence, because this star probably is after the TAMS, we can observe just by own eyes that the combined effects of high amplitude fields and the presence of the secondary companion are stripping this envelope, and the mass is being lost from the system in a very, very rapid way. Okay, so stay tuned, because our paper is on the edge of submission. I hope in this month we will finally close this paper and send it to astronomy and astrophysics. Okay, that's why we think we have some evidence for companion-driven enhanced mass loss in this particular system. Okay, thank you very much for your attention, because it's really hot today, so it's also really hard to stay focused during any presentations. And now I will try to answer your questions.
Thank you very much. There's a lot of questions.
Thank you. Super cool. That's first one.
Because
it's on that side of
the
diagram, but I enjoyed a lot, and I have a lot of questions, but we will follow up later on. But actually, two main questions that I have is like when we talk about tidal wave breaking mechanism, could we see it somehow in radial velocity curve or something?
Yes, probably we should be.
Okay, so that's to discuss later on. And the same with the color changes. Should we somehow see it as well?
I think yes, because as I mentioned, this kind of phenomena connected with very strong gravitational darkening or brightening. Choose whatever you want. But yes, it should be visible in radial velocities. The question is how huge this effect will be. I don't know. I can only guess. But with Phoebe, if you will change the mesh, you can estimate this effect because we can inject some artificial mesh to Phoebe, I mean some hour mesh, and then populate it with temperatures and calculate the light curve. So I think it won't be so difficult to simulate this effect in Phoebe even.
That's very interesting. And the other thing about the with collision with like collision cone, right?
WWC cone.
Yeah,
Okay.
Yeah. So because you said you've checked the various colors light curves and they don't really change. Let's say.
You mean this particular slide, this one, yes, from LCO.
So shouldn't the wind collision cone affect the various colors? Is it independent?
No, because this extra light comes from the scattering, this Thomson scattering of the light primary component. So you just have an extra light, maybe this WWC cone acts like a multiplier of the flux coming from the primary component, because this is a pure reflection, I mean the pure scattering of the lights. There is some additional effect connected with emission lines, of course, because we have many emission lines arising from this region, but these are only lines. So if you have very broad filter, this effect connected with emission lines, I guess it will be at the level of few percent only, and not at the level of, for example, 50%. Yes. Yeah, because this back injecting of the light by this WWC cone is really huge. It's at the level of 50%. So it's a huge effect.
So are there any measurements of the metallicity in this system with extreme wind?
In this XEV or generally in this one, exactly in this one? No, unfortunately not. We assumed a typical range of metallicities observed in Large Magellanic Cloud, but it's really hard to model the metallicity in hot stars because we have just a few lines in this spectrum, and that's why we can't tell anything about the metallicity.
Another question is, in certain extreme mass loss rate, and the mass loss should also affect the orbit.
Yes, it's observed, yes, with Marcin and Milena, because that was your part of work in our paper. We measured such changes, and they are high, and they are consistent with this kind of mass loss rate, because I've already checked it. Yes. So they are consistent, but it's hard to tell if, because we have many phenomena which are combined together. For example, we have TOs. We have equilibrium times, we have mass loss, and we also can have some contribution coming from the ellipsoidal motion. So, I'm sorry, so to decouple all of this, disentangle of all of this phenomena, it's really hard, and we cannot say if this rate of orbital decay is only due to mass loss observed in the system.
And the rotation of the stars?
We only know V times sinus I, of course, and we have an inclination angle. So the rotation is quite normal. I mean, it's well below the critical velocity. But it's not, of course, we don't have any kind of synchronization in the system because it's eccentric. So there is no synchronicity between the component and the object.
So is the system going to explode first or merge first?
I think if this mass loss rate is so high, we will have a typical situation where there is a main sequence star, and a street star burning hydrogen in the core. So I don't know what will be the further evolutionary scenario. I can only guess, but this is the situation where we observe pre-stripped star system. Yeah, I can.
That in the future can mimic this compact companions.
Exactly.
Right. There was a question on Zoom from Pavel. Pavel, let's try if we can hear you.
Yes. Hello. Did you hear me?
Yeah.
Yes.
Very nice. Yeah, nice talk and very nice results. Thank you. I have a question regarding the MESA isochrons and the last slide about the extreme blue variable. Could you go back to that?
You mean the slide with evolutionary tracks? Yes, from MESA.
Yes. Yeah,
okay,
this one, yes. So yes, to get the mass of this target, the metallicity would be valuable. Yes. And do you know the metallicity for this target from?
No.
Maybe
so these results, which I am showing you on this particular slide, is the effect of simulations. So we have some priors on metallicity, mass, rotation rates, and this FOV. Oh my gosh, it's the parameter describing the overshooting from the stellar core.
Convective zone.
Yes, exactly. And so we simulated all these tracks thanks to these priors, and we are just looking for this, which in the error bars are crossing the position of our star. So as you may see, the range is really broad. I mean,
okay, so as I understand properly, these evolutionary tracks are not for the same metallicity.
No.
For
there
the
is there is a Gaussian prior, which was involved in the simulations. Yes, we have a Gaussian prior.
So the next step is to get the spectrum and compare the metallicity with these tracks.
No, we had many. In our institute, we have such a PhD student, Tomasz Różański, who is dealing with stellar spectra and atomic data. The problem is the atomic data for example, carbon lines or nitrogen lines are so uncertain that we have huge doubts when we are making such modeling. So it's not enough to just take a spectrum, for example, from Lanz-Hubeny or O star, B star library of spectra and to fit the spectrum. Yes, it's not enough because the uncertainties connected with atomic data are so huge for many lines that sometimes we cannot say nothing about the metallicity. This is the main problem currently with modeling of this stellar spectrum. Yeah, that's not so simple.
Okay, thank you.
Okay, thank you. I think we're running out of time, so let's thank our speaker again. Thank you all for joining, and goodbye. Thank you. Just stop this.